Swayam Prabha. Digital India. Educated India.
Hello student. So, in this class we will solve some problem using differential evolution. In the last class I have shown you how you can solve a unconstrained problem. So, unconstrained problem using differential evolution. In this class we will solve some constraint optimization problem using differential evolution. So, we will mainly consider three problems here. The first problem is a minimization problem. It is a minimization of f x. So, it is a function of two variable, that is your x 1 and x 2 and x 1 minus 2 whole square plus x 2 minus 1 whole square. The unconstrained optimal solution of this problem is 2 and 1, but we have 2 and 1. So, somewhere here. So, this is the unconstrained solution of this particular problem, and but we have two constraints here, that is x 1 plus x 2 minus 2 is less than equal to 0 and x 1 square minus x 2 is less than equal to 0. Okay. So, this is the first constraint, that is x 1 plus x 2 minus 2 less than equal to 0, and this is your second constraint, that is your x 1 square minus x 2 less than equal to 0. So, therefore, the solution has to satisfy these two constraints. So, therefore, the constraint optimal solution of this problem is somewhere here, and the solution is 1 1 and the function value is 1 f x. So, we will apply differential evaluation to solve this problem, and we should get this solution, that is x star equal to 1 1 and function value at optimal solution is equal to 1. So, this is the first problem we will solve using differential evaluation. The second problem is also a minimization problem, and the function is 3 x 1 square minus twice x 2, that is your objective function. So, and if you minimize it, so then you should get solution somewhere here. So, for this range, that is x 1 is varying between minus 5 and plus 5 and x 2 is varying between minus 5 and plus 5. But there are two constraints, one is a linear constraint, that is your twice x 1 plus x 2 equal to 4. So, this is the linear constraint. So, that is twice x 1 plus x 2 equal to 4, and we have one nonlinear constraint, that is x 1 square plus x 2 square less than equal to 19.04. So, this is the constraint, that is x 1 square plus x 2 square less than equal to 19.4. Okay. So, if we solve it, the constraint solution is minus 0.2. Okay. So, this is somewhere here, this is the constraint solution of this problem, minus 0.2 and 4.4. So, this is the optimal solution, and function value is minus 8.68. Okay. So, this is the function value. So, we will apply DE and try to get this constraint optimal solution of this problem. The third problem is also a minimization problem, that is x 1 minus 3 whole square plus x 2 minus 3 whole square. So, therefore, the unconstrained solution is somewhere here and the solution is 3 and 3. So, this is the unconstrained solution, that is x star equal to 3 comma 3. Okay. So, you should get this solution, but we have a linear constraint here. So, this is the constraint, and this constraint is twice x 1 plus x 2 less than equal to 2, and therefore, the earlier solution is infeasible solution. Okay. Once you are putting this constraint, and the constraint solution is somewhere here, and this solution is -2 and 1.6, and function value is 9.8. So, we will apply differential evolution on these 3 particular problems. So, we will try to solve these 3 problems using differential evolution, and we will use R platform. Okay. So, let us see, we will try to solve this problem using R. So, I have opened my R Studio. So, let us open the file problem 1. So, this is your problem 1 file, and so what I need basically, I need D optim. So, I am putting require D optim. So, this is the library I need, this is the software package I need basically. So, I am putting that one. So, these lines I have written to plot the function. Okay. The function is that is x1 minus 2 whole square plus x2 minus 1 whole square. So, this is the function, this is the function of x1 and x2. So, let me execute these lines. Okay. So, I need DE, and then this is the function. Okay. And now, I have to create the value for x1 and x2. So, x1 is varying between -5 and +5, and I have taken a grid size of 0.1, that means interval of 0.1. So, and I have used sequence function. Okay. So, you can see what is x1 here. So, this is your x1 and this is your x2. So, both are from -5 to +5, and then I have calculated the z value. So, this is the z value. So, I have used outer function here, and so outer x1, x2 and fp. So, this is the z value I am calculating at each grid point. So, this is the z, and then let us plot the contour. So, contour you can plot. So, this is now z. So, contour I have written x1, x2, z. Then number of contours are 100, I put color blue, then label I am putting x1 and x2. So, if I executed this particular line, I should get the contour. Okay. So, this is the contour I am getting, and then let me plot the constraint. So, by this line, this is constraint 1. Okay. So, you are getting the constraint 1, and similarly you are getting the constraint 2. Okay. So, optimal solution is somewhere here. So, I have plotted this particular function. So, let me get the unconstrained solution of this particular problem. So, this is the unconstrained function. So, let me execute this one, and so this is the constraint function. So, I will discuss this later on, but let us solve the unconstrained problem. So, this is the function for solving the problem. So, here you have to define what is function. So, already I have defined. So, f is this f I have executed. So, therefore, this is the unconstrained function. Lower bound is -5 and -5, upper bound is 5 and 5, and I have not defined the other parameters. That means, I have used the default parameters. Okay. So, let me execute this particular line, then okay. So, I have executed up to 200 iteration, that is the default value of iteration, and now let us plot the optimal point. So, optimal solution is somewhere here. So, this is the unconstrained solution of this particular problem. Now, let us define the constraint here. So, this is the constraint function. So, what I am doing here, this is the unconstrained function f1, and this is the g1. So, g1 is x1 plus x2 minus 2, and g2 is x1 square minus x2. Now, I have used if else function. So, if else that g1 is less than 0 and g2 is less than 0, that means constraints are satisfied, then f will be your f1. So, else I am putting a very large number. So, that means I am minimizing this function. So, therefore, I am putting a very large number. Okay. So, this is my constraint function. So, what it will do, what this function will give, if there is no violation, so it will give you f1. or if there is a violation. So, it will f value will be a very large number. So, therefore, that solution will be avoided. So, let us execute this particular function. Okay. And now, I would like to rerun my differential evolution with this constraint function. Okay. So, I got the solution. So, let me plot this. So, you just see now I am getting the constraint solution. So, you can see that. So, I am getting the constraint solution of this particular problem. So, earlier solution was this, that was the unconstrained your solution of this problem, and constraint solution is here. So, I am getting that solution, and if I would like to see, so I can see the summary of RES. So, you can see that whatever solution I got, this is 1 1 and function value is 1. So, anyway, so generation is 200 generation and function evaluation is 402. So, I am getting the solution of this particular problem. Okay. So, anyway, so I can handle the constraint within this particular function. Now, let us solve the next problem. So, let me open the next file. So, that is your problem 2. So, here the objective function is 3 x 1 square minus twice x 2. So, this is the objective function. So, I required d optim. So, then let me run this objective function, then x 1 and x 2. So, x 1 and x 2 both are varying between minus 5 and plus 5. So, let me generate the value of x 1 and x 2 and then generate the value of z. Okay. So, this is I am generating the value of z, and then let me plot the contour map, plot the contours. Okay. So, if I execute this particular line, so I am getting this contour, and as I said that minima of this particular function is somewhere here. So, I can plot the constraint now. So, this is the constraint, first constraint, that is the linear constraint, and this is the second constraint, and optimal solution is somewhere here. Okay. Now, let us define the objective function. So, objective function here is f1. So, for solving for using DE, so I have to define objective function in this order, that means x has to be a vector. So, f1 is 3 x 1 square minus twice x 2, then g1 is twice x 1 plus x 2 minus 4. So, this is the linear constraint, and g2 is x 1 square plus x 2 square minus 19.4. Okay. Now, so here also I have used if else function, if else the g1 is less than 0 and g2 is less than 0. So, in that case it will give f1. So, it will take f1, that means if constraints are satisfied. So, f value will be equal to f1, that means objective function value will be f1, and if it is not satisfied. So, I am putting a very large number, that is 1 e to the power 4 in that case. So, that solution will not be selected. So, when you are going for a selection operator, so this solution will not be selected. Okay. So, let me execute this particular function. Then here I am using the differential evolution, and I use the default value, only I have defined the lower bound and upper bound. So, lower bound is minus 5, upper bound is plus 5 and plus 5. So, let me execute this one. Okay. Then I am getting the solution. So, let me plot this solution. Okay. So, I am getting this particular solution, and I can see the summary. The base solution is minus 2 and 4.4. So, this is the solution, and objective function value is minus 8.68. So, I got the exact solution of this particular problem, and you can see that D is quite effective in solving constraint optimization problem also. Okay. So, you will get the constraint optimal solution of the problem, and it is quite efficient. So, I can also solve using ZA. So, if you want, whether you are getting this, in that case you have to include the ZA library. Okay. So, I am not doing that one. Okay. So, I am getting the solution of this second problem. So, you can see that I got this solution. Okay. Solution is on the constraint boundary. Now, let me solve the third problem. So, this is the third problem. So, here again I have plotted this particular function. So, let me delete this. Okay. Let me clear all the space. So, now this is the objective function. Objective function is x 1 minus 3 whole square plus x 2 minus 3 whole square. So, this is the objective function, and I am defining x 1 and x 2, and x 1 and x 2 are varying between minus 5 and plus 5. So, let me generate x 1 and x 2 values. Okay. Then calculate the z values. So, I have used outer function. Okay. Now, plot the contour. So, this is the function and optimal solution, unconstrained solution is somewhere here. Let me plot the constraint function. So, there is only one constraint function, and that is a linear constraint. So, I have plotted this one. So, optimal solution is somewhere here at this particular point. Now, let me define the constraint function. So, this is the objective function, and the constraint is g 1 equal to twice x 1 plus x 2 minus 2. So, this is the constraint, and here also I have used if else function. So, if else, that means if there is no violations, then this function will return f 1, that means I will take f 1, and if there is a violation, so in that case I will take a big number just to avoid this particular solution. So, you execute this particular function. So, I have executed that one. Now, I am using DE optim. Okay. So, again I have used the default values. Okay, it is done. So, let me plot the points, optimal point. Okay. So, this is the solution of this particular problem. So, I can see the summary of this solution. So, base solution is 0.2 and 1.6, that means this solution is x equal to 0.2 and x 1 equal to 0.2 and x 2 equal to 1.6, and the function value is 9.8. Okay. The function value is 9.8 and generation was 200 generation, and function evaluation was done for 402 times. Okay. So, this is the solution of this particular problem. So, you can see this is the constraint solution of this problem, but if you are solving unconstrained, so but if you are not considering this constraint, so you should get this particular solution, that also you can check. So, I will only use this particular function. Okay. So, let me check this one. So, this is function x. Okay. So, let me check this one. So, if I execute this one, then I will execute the D optim, and then let us plot this one. So, you just see I am getting, now I am getting this particular solution. Okay. So, this is the unconstrained solution of this particular problem, and if you are putting the constraint, you should get this particular solution. You can see the summary. So, now solution is 3 3 and function value is 0. So, that is this is 3 3 and function value is 0. So, in this class we have solved 3 problems, and basically we have solved the constraint optimization problem. So, you can apply the same DE. So, D actually you cannot define constraints separately, but in other cases in some other algorithms, so you can define the constraints separately, but in this case you cannot define it. So, this particular package can handle the unconstrained function. So, therefore, you have to make your function and convert, and you have to make your function and convert the constraint optimization problem to an unconstrained optimization problem. So, in this class we have converted it something like that. If there is a violation, we are putting a very large number because the problem is a minimization type problem and I would like to avoid that solution. So, if there is a violation, so I am putting a very large number in order to avoid that solution, and if there is no violation, so in that case it will consider that particular function value. Okay. So, let us stop here. So, in the next class we will discuss some other problems. Thank you.